According to the CDC, there's more than 40,000 births per year that are affected by congenital heart defects. These are defects that infants are born with, which motivates a lot of research into this area. Hence why the International PC4 database was created, in order to collect CHD patients' data and use it for research. However, the data collection process can be very tedious. Say you have this clinical note and you want to extract these pieces of information from the note. Say it takes you around 10 minutes. Say you have more than 6,000 notes a year. That's going to take you more than 1,000 hours per year, which is very time-consuming for nurses, which is a problem that Texas Children's Hospital has. Hence why we're collaborating with them to develop an NLP algorithm that can expedite the process of uploading the data into PC4. That can allow us to do more than 6,000 notes in less than 2 hours. That can greatly decrease the amount of time nurses have to spend on the computer and greatly increase the amount of time they're able to support patients.
There are a total of 9 different entities that we have been tasked with extracting. These entities fall into 3 different categories: numerical data such as birth weight or birth length, Boolean data such as whether or not a patient was born prematurely, and description type data such as what chromosomal abnormalities a patient might have. This now brings us to the data pre-processing step in our data pipeline. Many patients have multiple hospital visits over many years, with a new clinical note created for each visit. Medical record numbers, or MRNs, are the only unique patient identifier that remains constant across multiple hospital visits. The very first step of our data pre-processing is to sort all of the clinical notes by MRN and combine them into one singular text for each patient.
But in order to use these clinical notes in training, we actually have to find where data points occur within that clinical note. We have 2 different methods where first we can just take the entry that is within the Epic database and try to find it within the respective clinical note and then extract where it is, or we can use rule-based NAR where we look for common patterns for that field and extract any values close to it. Additionally, we now have over 5,000 patients total from which we can get data from. Previously, we only had about 2,000, so hopefully this will improve our results.
Once pre-processing is complete, the next step of our data science pipeline is modeling or extracting the named entities. And to do this, we use a Python library known as spaCy, which is a state-of-the-art NLP framework. Our spaCy model takes in labeled training data, as shown on the left, and uses a transformer to create word embedding vectors. Then, the NER step learns the weights of a neural network, which uses LSTM, long short-term memory cells, in order to preserve meaning across sentences and paragraphs. In order to improve the performance of our NER model, we added a rule-based component built into spaCy between our transformer and our NER steps. The rule-based NER uses regex matching on all of the syndromes, chromosomal abnormalities, and non-cardiac abnormalities listed in the PC4 manual in order to label any low-hanging fruit before it proceeds to learn the neural network to complete the NER model.
This semester, we used medSpaCy, which is a wrapper around spaCy to tailor it for medical text. This wrapper lets us standardize medical abbreviations, which yields more consistent training data, as well as a custom whitespace embedder tailored for medical notes, which is useful as clinical notes are often irregularly structured. On the output side, this wrapper lets us filter out erroneous tags, such as the birth weight of 25%. The next step was to evaluate model performance. We used recon to evaluate the individual PC4 fields, which is a metric that emphasizes accuracy relative to the number of false negatives. And here we compare the spaCy and medSpaCy results. While overall recall went down, medSpaCy shows improvements in some entities, particularly antenatal diagnosis and birth weights. When we group entities by data type, we find that medSpaCy performs better on numericals and booleans. Numerical and boolean information is often mentioned in the form of lists, which feature irregular whitespace, which is likely why medSpaCy performed better on these entities.
As for bybird updates, we have recently discovered that bybird's tokenizer might cut 2 sentences in the middle of the word, which might decrease the accuracy of named entity recognition. To avoid that, we split the medical notes into 512 full tokens, similar to work that was done to spaCy tokenizer. We have also discovered 3 special tokens that bybird uses, which might be very useful for named entity recognition. The first one, CLC, marks the beginning of the input sequence. SEP is used as a period to separate 2 different sentences. Append is used to create the input sequences of the equal length, in case one of the input sequences is not 512 full tokens. Our main goal is, of course, to have a very high accuracy on rule-based NER and improve spacey, as well as finalize ByBird, but it's also very important to transfer knowledge to data analytics teams at TCH. To do that, we try to build very user-friendly interface and very robust and reproducible pipeline, such that when they get better data and larger data set, they can easily achieve better results with the current model.